Today we are in the class number 23, 7th of April 2020, and we are going to talk about the brace. The brace is actually a very important issue that we generally don't learn much, we don't understand much, and the art of this brace design is actually at the point where you don't really have the force that you know for the design. That's not just the force, actually it includes the stiffness in the design as well. So the brace controls the capacity of your structural member by the stiffness of the brace itself, and also by the capacity of the brace itself, and that enhance the capacity of the structure quite drastically. So it is a very cheap investment in order to gain a lot more. A lot more means like 40 or 50 times bigger than what you invest. And here is a very important issue. So you know how to design the column, you know how to design the beam, but the brace is going to enhance the capacity or ensure that you are going to achieve the capacity you wish to have from the beam or column by the appropriate sizing of the brace. So this paper is authored by George Winter, and this was published in 1960, and that is roughly 80 years ago. This is year of 2020, so it has been like almost, it is about 80 years. So the introduction of this paper is actually talks about the brace that are available in the world. There are practically two kinds of brace, and the first kind is the brace that actually the force magnitude for the brace design. So what could be that? You might have things you see in the earthquake or wind engineering. You have sort of building, and you might your structure might experience the lateral force caused by the wind or the earthquake, and you have the brace that installed in order to control the lateral drift, in order to enhance the capacity of the structure against the lateral motion or lateral excitation. You apply the brace like that. And as you learn dynamics of structures already, you learn the earthquake and wind already, you know how to figure out the lateral force. So knowing that, you put it in the structural analysis program, and you will get the magnitude in the brace. Okay, so force magnitude can be determined, and you can design the brace. This kind of brace is not interesting for us. It has nothing to do about the stability of the structure. It is designed to resist the load, and for that reason you can do it. You know how to do it already. The brace of our interest is the brace for the instability. We provide a brace such that the instability of the column or beam will be resolved by increasing the lateral restraints against lateral displacement and so on. You know how the beam fails, you know how the column fails. We learn about the limit states of all these elements, then you understand what needs to be restrained in order to achieve the capacity. Now we can just skip the introductions, many things. So this paper actually comprises two main things. The first part of this paper talks about the experiments, and the experiments here actually you can you can look further if you wish by going into this paper. So this one here is actually just the report, but it talks mainly about the experiments which is done, and it is documented in here in the paper here. Okay, Green Winter and that guy. So this one. So the experiment is carried out and very well documented in here. You go look up, and if you can find, just send me. I don't spare my time to look for that up. It is actually quite enough for here. The information is very well documented here already, but it doesn't include every single thing they did. So only some specimen result from some specimens included in this paper. Basically, the experiments was carried out, and how was it carried out, and what was carried out. The buckling load testing of the column was tested, and the column that they test is actually the I shape 4-inch deep and 2-inch wide. It is made of 2 channels co-form of 16 gauge. Okay, 2 channels co-form, this one here. So this is one channel, another channel. It is a light gauge steel. It is not that thick, and so it is possible to co-form into the channel shape. And they took these 2 co-form and welded them together such that it forms the I cross section, like the Y flange, I beam. Right? 16 gauge sheet steel are spot welded back to back. Spot weld means they don't make like a through welding from one end to another. It is not that necessary to do that, and it's gonna cause like too much heat, and you end up with the residual stress problem. I shape 4x2. They were tested as column of 12 feet 3 inch long. 12 feet 3 inch. 12 feet multiplied by 30 centimeters, you end up with 3.6 meter, and 3 inch. Okay, so 3.6 something meters, less than 4 meter, but it is very slender in comparison with the dimensions given here. The big one is 4 inches 10 centimeters. This one is 2 inches or roughly 5 centimeters. So you compare between, like, the aspect ratio is 3 point something divided by 5. So if we do like a 360 divided by 5, then you get the 72. Just the aspect ratio. Hey guys, if the sound quality is okay, please let me know. Or if it's not okay, please also let me know. Don't bear with it. If I can fix anything, I will. I can just check the configuration of the parameters in the program. If everything is okay, then I just continue this way. Then as you can see that the specimen is very slender, so they want to test, well, of course they want to test the breast, so they design the specimen to be very slender, and the breast is later installed. So first of all, the one of the specimen, one of the column. Okay. Oh, I just now I get to see the comments. Why in this specimen, why they use the cold form? Okay, I get one question. Why they use the cold form instead of hot roll? Well, the hot roll specimen, you can hardly find this small size cross section of which the flange is as small as 5 centimeters. In the market, the cross section like this might have the it is available for the 100 by 100, but 100 by 50 it could be very heavy section still if you consider the thickness of the flange and the web. And okay, everybody, I think I get a okay, sound quality and picture qualities are all good, so thank you so much for the comments. I am relaxed with the with your input, so yeah, the recording is going to be a nice one. Okay, so that's why they forms up the cross section by using the cold roll, and the intention is just to study something which is light enough and it will not need so much bracing force. You will see what how the bracing was carried out in a bit, yeah, in this moment actually. So the specimen, which is very slender and pretty light, was test, the column was test, and the support is the knife edge. It's a knife edge support. As I used to tell you that for steel structure, if this is a column, they produce some sort of very sharp edge like this at the top and at the bottom, such that it restrain no moment. It produces the condition which is pretty much like the hinge condition. So well, we are dealing with the stability issue, and everything counts. So to make sure that all the boundary conditions are going to be posted accurately, the very neat boundary condition is then the requirement. So the knife edge support was used to represent the pin boundary condition, and then one of the column was test unbraced. So this one is the control specimen. One of the column was tested unbraced. So the control specimen, they let it buckle at the low axial force because it is not braced. For other identical specimen, identical means the Y flange, the I-shaped cross section is identical in the geometry. Intermediate bracing was provided at the equidistant points. And how does that look like? So we'll see. Specimen looks like this, and you have basically it's like a pin, right? So it is like a pin like this, and secure it and this. So the load was applied. They use the UTM to apply axial force. So this axial force was measured. The thing is that this is the first specimen they tested, and it is braced. So equidistance. For example, if they put one pair of brace, why do we call a pair? It's gonna be the left and the right, so it is called one pair of brace. So if one pair is installed, it looks like this. If it is two pairs, then you're gonna end up with this configuration. So the keyword is the equidistance. Equidistance point. That means this is going to be L like this. So you have the equal distance, equal length that the brace separates the zone into n numbers. Okay. This bracing at each point consists of two strips of thin 10 ply 10 ply cardboard. So it is made of the cardboard. Cardboard is like the paper used to make the box for the shipping, like that. Yeah, it's a cardboard 3/4 inch wide. Okay, so all the brace they provide made of the cardboard, of which the width, the width are all equal to 3/4 inch, made of the same thickness. Basically, the cross sections are identical. The only difference about the length of the cardboard. So let's see it here. If the cardboard it could be 2 inch, or it could be like very long 15 inches. So what do we get from here? It means that we are testing the system under the different brace stiffness. EA is constant, material is the same, cross section, the width is the same, the thickness is the same, but the L is non-constant, so it is 2 or 15 inches. So the sensitivity of the buckling load of the column to the stiffness of the brace will be shown in the test result. And with the same size of cross section, 10 ply cardboard 3/4 inch wide, that means the capacity, the brace capacity, okay, it turns out to be are identical. So generally the cross section controls the capacity, right? So if we use the same cross section for all braces that is installed to the column, that means the capacity of the brace of every case identical. So the difference is only about the stiffness of the brace. The tensile strength was 103 pound per pair. 103 pound per pair, and this is just uniform for all cases. Figure 1 show one of which line? The studs under the test with 4 pairs of strips in place, and the right part a portion of failed specimen with 2 pairs of broken cardboard strips. Okay, you're gonna see the picture, and the picture is not so clear anyway, but these photos happen to show the strip of which the width is 1.5 inches. Actually, is from this paper, and I told you that they don't include all the information from this paper in this document into this paper here. But okay, maybe by chance the figure is just available over here. Just this piece of specimen is taken. The table 1, okay, which is going to be in the next page, is gonna shows everything relating to the test result of the breast. Anyway, let's just just read through this first before we go to the next page. In this test, the usable strength of column could be increased as much as 15 times by using bracing as weak as that provided by the described cardboard strip. They use cardboard in order to just to show that even just the cardboard, which is like a paper, just only the paper, it can be used to brace the steel column, and that improves the strength of the column to as much as around 15 times. But okay, 15 is just a number. Is it a big number or is it a small number? We're gonna take a look at it and get some sense of it. And here is the test description, and you can see pretty much nothing because the picture quality is really bad. It is in black and white. I hope that when you take picture from for your research, you should do something which is much better. Well, this is about the publication as well, so when the picture is published in black and white, it is printed into very low quality in the past. So the big frame here is the UTM, Universal Testing Machine here, and the center column here is the test specimen. It is a tested column, and the test column is supported at the top and at the bottom by the knife edge hinge that gives you the very accurate boundary condition. This boundary condition just allow the rotation about the weak axis only, as it is a knife edge. That means it is like a strip, it is a line support. So the rotation about the strong axis was not allowed, it is prohibited. And at these arrows, I think you can see this strip, and these strips are the brace that I mentioned. So these are made of the cardboard, they are the cardboard strips. And this picture on the right actually shows the broken brace. So they mentioned already, but we can hardly see of this failure on the specimen very clearly. But forget about it. I think you understand what went on in the experiments already. I think my energy is a little low due to the last night teaching. I figure out that it has been 2 hours and roughly 2 hours and 20 minutes for the last night teaching for finite element homework. so it was a little long, and yeah, that I don't regain the energy back yet. Look into this table. So several columns were tested. All columns are having the same length, the same cross section. So the only different parameters is about the bracing. And the test number here, you don't need to care about it. It is just the ID of the specimen. So just if you are interested, really interested in this information, I'm not sure, as it is not the paper, I'm not sure if you'll be able to find this, but that might be available through the open library, online library of the Cornell, right? I think it is Cornell University. Oh, Cornell. I'm not sure. Cornell. If it is Lehigh, generally Lehigh open this steel research, all paper for free, all documents. I'm not sure about Cornell. Never get one from Cornell. Anyhow, come back. So the test ID is given. Don't care about it. We just look at this information first. This information describes the brace that were applied. So first of all, the number of pair was given. The zero pair means what? It means the column is unbraced in between the support. So it has nothing, and that is the control specimen. So the length of the brace is not given because there is no brace. And then what you obtain is that the load is now in pound. Okay, in pound force, how much? 1098. It is equivalent to probably half a ton, half a metric ton. So this is the ultimate load of the column, buckling load of the column, maximum, let's say. And okay, there is nothing about the brace strength in percent of the column strength. Failure, it is just the column buckling. Now we move to the next experiment. The next experiments improve the quality of the column by installing one brace. One brace, then the column, it used to have the unbraced length equals to L. It used to have just L, right? Now the unbraced length is reduced to L over 2. When the unbraced length is reduced to half, what do you expect for the capacity? You expect pretty much 4 times the capacity from the previous case if this is 1. Why? 1 means 1 time of pi square EI over L square. You have the simply supported the pin column. So the K is 1.0. So if the first one forms the pi square EI over L square, the second one, if you have the very stiff brace like this, effective length of the column reduced to L over 2, and as it reduced to L over 2, you plug in L over 2 in here, you end up with the 4 pi square EI over L square. So 4 is this number. It is obtained from that. And then the increase more number of bracing points, so they have the two pairs, and for these two pairs, one specimen they have 15 inches length, and another one is 4 inches length for the brace length. This is to vary the stiffness of the brace, whereas the capacity of the brace is still maintained to be 103 pounds. And now, as the unbraced length is shortened down to L/3, you expect 9 times higher. If you can produce the condition like this, this is the full brace condition. So full brace condition is the condition that you can mobilize the capacity of the column to the ideal values computed from this structural model. And then more braces were installed in the other specimens. So now you have the 4 equidistant unbraced lengths, and that makes the column stronger by 16 times. Lastly, you install 4 brace locations and making the unbraced length to be L/5, so you expect 25 times higher for the capacity. Then now we come back to see the result from the measurement. The measured result is the ultimate load in pounds. So the capacity of the column is recorded for each individual case, and you can see that first case it is roughly about 1100, 1098. It is pretty much about the 1100, and of course this is an experiment, so you expect some discrepancy. The specimen might be prepared differently from one to one. And actually another reason why the cold form was used is because the cold form cross section, the control of the dimension is easier. The tolerance of the dimension is less as it is cold formed, so it is easier to control, and it is easier to get pretty much the same geometry rather than using the hot roll steel cross section. It is very precise for the cold form if you used to see the difference of the cross section between cold and hot roll, cold form and hot roll. So that's the case. Still, okay, you should expect some error or discrepancy from the experiments anyway. Sometimes the force measurement at the low load like this in comparison with high load like there, your load cell at that time it might not be the load cell, it might be just the pressure gauge reading. So the pressure gauge is calibrated with the proving ring in order to obtain the force magnitude. And this system you can see in our lab, we still use the Shimizu testing machine and for the compressive strength crushing testing, etc. The point is that the pressure reading is going to be converted into the force, applied force, and the discrepancy is expected over there. The machine reading, the gauge, all these testing instruments generally cause some error, especially at the low load zone or low load magnitude. If you have the equipment that measures a very wide range of force magnitude, for example, if you have the load cell for 100 metric ton, maximum capacity, and if you use it to measure the load, which is around 1 or 2 tons, the resolutions will not be so good because it is by design, it is made for high load. So if you measure small load, you better use the small load cell. You don't use just a high load cell, and each increment's reading is going to be very coarse. So back to our business here. First, unbraced column produce the 1100 pound capacity at the buckling. And when you look at the test number 2, the second one, the test number 2 over here, what you get is roughly 4,600 pounds. This 4,600 pounds is, well, if you think of it like the 4 times of 1100, that 1100 could be, the actual number could be 1160, 1150, whatsoever, but told you the discrepancy is always there. But it gives us the guide number, the guideline number that the jumps is about 4 times as much as the unbraced length capacity. Okay, so it is quite consistent with the theoretical prediction that 4 times is expected. Now we come to the next step. So the number of pairs of braces furtherly increased to 2 pairs, and then you have the L over 3 equidistance. The thing is that this case here, as you have the longer strip, the longer cardboard strip, you expect less stiffness, right? EA over L, that is your stiffness, and EA is constant, L is longer, then you get less stiffness, whereas the 4 is giving you higher stiffness, not as deformable as the 15. So let's take a look here. As the unbraced length is reduced to L over 3 for both, you expect that both of them should gain the strength as much as 9 times of the original unbraced length. But here is the result. You get 9,900 and 8,600. These two numbers are not the same, and the difference is quite significant. The difference is about more than 10%, about 15% roughly. This is about 10K, and this is the 86, so it is about 13-14% which is huge. And let's look at this one first. This one, as the stiffness is higher due to the shorter length of the brace, you gain the strength up to 9,900. 9,900 is approximately 9 times of 1,100. So this match with the theoretical prediction that strength should be gained up to this far. So the system here, we provide sufficient stiffness of the brace, so it can the overall system can gain the strength up to the full bracing strength, whereas the low stiffness system over here produce less than the theoretical value of 9,900, and that is because of the stiffness itself. As you have less stiffness, the system or the column can deform more, and as the column deforms, the more deformation, the more force, right? More deformation, more bracing force, So as the bracing force is more, strip breaks. More than this one. So the twin of this case has higher stiffness, has a higher brace stiffness. So the higher brace stiffness prevents the deformation to be too large, and then the force is not high. And as the force is not high, then the strip does not break. It didn't break, and then the column buckle, you have a full mobilization of the column load. Okay, this column here records the percentage of the brace strength compared to the column strength. So the brace strength is 103, as I told you before. And the capacity of the column is taken from here, measure ultimate load column. Okay, so you take these two divide, and then you get the fraction, and it turns out to be the percentage. So you multiply by 100. Okay. You can see that for the first case, the percentage is high, and then the percentage is reduced and reduced and reduced, okay, as the column load increases. By the way, the 103 is for just one strip. Okay, this is the capacity of each brace. It's not the summation of braces. Like this case, you put two pairs and then it turns out to be 206. No, it doesn't work that way. It is just the number for one single strip. Okay, and then we can see this figure here, that the case where you have less stiffness, you have the higher bracing force ratio compared with the capacity, right? Bracing to the capacity, column capacity ratio, it is higher than this counterpart. But actually the brace force is controlled to be 103. The difference is caused by the 103 divided by the 9900. The denominator is changing, but the numerator is maintained to be the same. Then we move over to the next case. The next case, we have three pairs of brace, and again the three pair of brace, I think the reason why the brace length is shortened down to 2 inches because the 4 inches didn't provide enough stiffness, so the 2 inches was used for this comparison. And here two different stiffness. The stiffness are different by roughly 7.5 times. So this one is 7.5 times stiffer than the one above. And 3 bracing points make 4 equidistances, and that is corresponding to 16 times of the capacities that you expect, because unbraced length is L over 4. So you see from 1100, if you multiply by 16, you'll be, well, around 17. It should be around 17 and 6, like this. Approximately numbers should be around here. But you find that it is just around 15 17,200. Okay, not too far from 17,600, but still this is less than that number quite significantly, and that is because the brace stiffness of 2 is not that enough. And you can see over here that the recorded failure mode, and this is important when you run the physical specimen testing. The failure mode should be well recorded, very well recorded, and then the analysis of the failure mode is gonna give us a lot of information. So if you by chance run the physical specimen testing, if it is the RC, then you're gonna record the crack, you're gonna see the crack, how it start, where it start, how big is it, what kind, you got to categorize the crack, flexural crack or shear crack, or is it caused by the splitting and that caused the longitudinal cracking, right? Is the rebar buckle, is the rebar yielding, all of these failure of individual material has to be well recorded in order to understand the phenomena and understand how things fail in the structural engineering point of view. And this just explains us this idea, this information very, very well, because the strip broke for 2 cases, and that is consistent with the lower load than the expected value, of which it should be around 17,600. Okay, but we can see the very nice improvement from 10 to 15, which is 1.5 times of the 10. So the brace stiffness, if it is just increased, and you get a bunch more capacity for the column. And you can see that this case you need actually the 103 is the same, but the capacity is more. So the ratio between the required brace stiffness, brace strength to the capacity of the column is reduced from the low stiffness case. Okay, so this is a very good piece of information. We can see the dynamics of this issue. And the last one, it is sort of weird, column buckle, but strip doesn't break. But it might be the more global column buckling. I don't have the very detailed pictures of this column buckling. Anyhow, you are expecting 25 times more than usual, more than unbraced case. So you expect like 27,500, but none of these can gain to that far. And well, you are talking about cardboard of which the capacity is just 103, is bringing you up to somewhere around this, which is about 100 times bigger in capacity, more than 100 times. It is about 160 times of the cardboard capacity. So it is a very cheap investment that pays you off very, very well, and that's why we need to look at it. The thing is that how do we determine the appropriate capacity of the brace, and how do we determine the appropriate stiffness of the brace? That's the thing. For the world these days, you might just use the Excel spreadsheet with the the geometric nonlinearity analysis. That could be used as well, and it needs less brain and less assumption than this paper, but imagine 80 years ago when you do not have the calculator and the slide rules were still used back at that age, and no Microsoft Excel, so they cannot find the buckling load by the technique that we can do these days. So we can try our stiffness, geometric stiffness spreadsheet for the buckling load determination with the given stiffness of the brace, and the brace will be represented by just the side spring. Okay, so let's look into this conclusion from the test result. In those tests in which column failure was accompanied by fracture of the bracing strip, the strength of one brace was of the order of only around 1% of the strength of the column. I told you it is a good investment, right? The efficiency of bracing depends not only on its strength, this is a good point, but also on its rigidity or stiffness. In fact, the strength per brace was the same in all these tests, 103 pounds. However, because the longer strip possesses proportionately larger extensibility, so yeah, just more flexibility. The shorter strip, the greater rigidity of the bracing. We know all this. ERL comparison of the pair test 8, 9, blah 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 shows in each case that the greater where is the line? Greater rigidity produced the larger column capacity. Okay, we saw that. In addition, test 8, 9, 20, 22 illustrate that other things being equal, the greater the rigidity of the bracing, the smaller the strength required. For this, we have the constant strength, and then we have the different column load. In contrast, if we decide to get the same column load, we will need less bracing strength, right? So the column that shows the ratio between the brace capacity to the column capacity, that could be used. It gives you the same interpretation. So they use the ratio required of it to produce a given column capacity. Indeed, in each of these pairs, the softer bracing broke, whereas the more rigid or the shorter bracing not only produced a larger column load but did not break at that load. Okay. Although the strips broke in both tests 15 and 16, it is seen that here two bracing of the same strength, the more rigid one produce the higher column load. Okay, blah blah blah. Right, so in principle, you have two factors that affect the column load after the brace. So the brace stiffness and brace capacity, each of them are controlling. Right, now it is possible. Okay, I think we can just skip that. Okay, another long paragraph. In here, I don't see much information that we need to go through. And this could be the reading you might need to look at. So, Theory of Elastic Stability by Timoshenko, Lateral Bracing Force on Beam Column, ASCE, Suk, I don't know who's. And this is the paper, not the paper, it's a Cornell, another Cornell dissertation. So it's a green, okay. This is Don't use this page now. Alright, so the author reflects the fact that when it comes to the design for a structural engineer, we need to know, what we need to know is what is the brace characteristics, either capacity and stiffness, such that we can just put the minimum number and gain the maximum possible capacity of the column. So you put too big brace, you don't get anything back, because you can see that the test shows that it is around a few percent in comparison with column load. So we need to find precisely by the analytical approach what will be the required brace stiffness to mobilize the full column force. Okay, so the question is much more simply to determine minimum rigidity. You don't want to put too much. That will make the actually elastic bracing equivalent in effect to the unyielding supported support. Such bracing will evidently produce maximum column load for the given location of brace or braces and will be called the full bracing. Yeah, this is the condition that is desirable. We need the full bracing. Maximum possible column load will be obtained from full bracing. From the data of Table 1, it is evident that relatively low rigidities and strength are required to provide such full bracing. Okay. So, now let's consider the column which is going to be used for the analysis for the formulation of the analytical solution to the brace stiffness determination. Should sleep more. I got up too early. Okay. Well, you can see working is not using much the brain that much. Teaching is the activity that consumes a lot of brain juice, because I have to think of the subject matter. I got to first convince myself about the subject matters, understand it under the fundamentals and mechanics of it, and then try to find the easy way. That's the first step. The second step is to find the easy way to change from what I understand to the easy language that will make you understand as well. That is the second step. And then the third step, that way, that approach will be turned into the language. So the language is the conversion from the scientific understanding to the linguistic understanding, and that is transferred to you. So that's the 3 steps. But in comparison, your brain is working at the 1/3 level of mind, because you are listening, then you just receive the third step of mind to your brains. And okay, maybe you have 2 steps, okay, and then you need to convert that linguistic information into the scientific information. But it is, for me it is like more than your part, more than the workload of your brains. And coffee doesn't help. This is the second big cup of coffee already, and it doesn't really help much when you run out of the brain. And to regain the brain back, you need to sleep. That's it. Now, okay, if an ideal column with hinge ends is furnished with an unyielding knife edge support at the mid-length, so it is, they refer to this one. Okay, furnished with the unyielding, with the support, which is just perceive that it is just a support. Okay, they put too much information. Okay, so column, and then with the mid support, what you get as the buckling shape of this case is like this. So the dotted line is forming the two, well, it is a full sine curve, right? Full cycle sine curve. So this is one half, and this is another two half sine combined to one full sine curve. Okay, so and this is what they mean. It buckle into half sine wave. Okay. At the intermediate support, the second derivative of y with respect to x, okay, just think of the moment then, right? As it is the inflection point, so the curve is changing from one curvature to another curvature. This is so-called inflection point, and you expect zero moment at that point, in which m is the moment of force. Okay, I is blah blah blah. You don't want to know this because you know this very well. Consequently, if a real or fictitious hinge, now this is the thing. If a real or fictitious hinge were introduced at the support in the continuous column as shown here, nothing would be changed. Of course, how would it change? Because this is the inflection point. Inflection point has zero moment, and with the zero moment, you can put the hinge there. Is that right? Huh? You're just simply putting the hinge there, and it could be the fictitious hinge, or if you put the real hinge, it doesn't really change your solution. Okay. And then, in particular, the column with or without such hinge buckles at the Euler-Chandler load. And that is the pi square EI over L square, and the L, alright? Please be careful, the L is defined by this unbraced length. If you call this as a L, then it's going to be the 4 pi square EI over L square. So this is just unbraced, unsupported length. PE is a column load, and where in the elastic domain E is a Young blah blah blah. I don't want to talk about that anymore. If the ideal column is braced by an elastic support and if this ideal column is braced by an elastic support, and if this support is rigid enough to provide full bracing, the column buckles in exactly the same manner as for unyielding support. And again, a fictitious hinge can be introduced at the support. Right, I'll come back to that picture and what they just said there. Said, well, you are convinced already that fictitious hinge can be introduced. Now it's fine. We advance to the next step, and the next step is about the support not rigid like this. It turns out to be elastic support. Elastic support means it is a spring support. Well, you see all of this. What is your view? You can imagine that the tools we developed in computer method in structural analysis can be used in this place here, right? We can run the sort of, I never tried this before, and actually it is another interesting issue to try. So make the column like this, discretize like this, maybe put some more, just this. Actually the Octave code could be used to construct things like this, because you don't want to do it in Excel. And then we put the spring. The point is that what Winters want to learn here, he is trying to develop and simplify the structural modeling techniques such that it is possible for just a simple formula, just a few unknowns, few displacement, degree of freedom for the consideration. But Microsoft Excel can handle more than that, so why not? And then the K can be varied. So the K can be varied such that you get the buckling load that is up to the full buckling, and it goes like this. So the K has to be big enough, just big enough. Then you just plot the K like this. K could be horizontal axis. This is P over PE, where PE is determined from this unbraced length. POPE was supposed to be just 1, right? So as the K increase, this goes up, and then hit 1.0, and that is your ideal. The curve might not go and then go flat, and then this is the K ideal. It could be done this way. We should try. Probably tomorrow we can try this. But okay, we are not going to. Still the closed form development is still very useful. So the elastic spring is introduced, and as this elastic spring is introduced, there will be possibilities that the column will fail, and these are two possibilities. First of all, you will see this line, the dotted line. It goes like this. Column has not buckled yet. It has the second order effect, but it's not mobilizing the full buckling load yet. It buckles even more, and then at one point it forms the double curvature, like in this solid line. So you have one curvature here, another curvature there, and then at the hinge point, it is the inflection point. Okay, so come back to this writing here. To obtain information for practical design of bracing, it is now necessary to investigate the real column. This is necessary because, as previously mentioned, the theory of ideal column would indicate that supports of infinitesimally small strength are sufficient, in which also come to here. So it will become apparent the minimum rigidities computed for full bracing of ideal column are not sufficient to achieve full bracing of real, that is, imperfect column. To simplify analysis, it will be assumed that column imperfections, eccentricity, curvature, and so on and so forth, can be represented by an equivalent identical crookness or the bow whose amplitude d naught is small as compared to L. Alright. Such a column with single elastic support is shown in figure 2D. As the column is loaded, the elastic brace, so this one is the initial bow or initial out of straightness or initial crookedness. Okay, the D naught, and then you load, then it is increased to D, right? As the column is loaded, elastic brace with spring constant K deflects together with the column as is shown in broken line with a consequent support reaction F equals to KD. If full bracing is provided, final failure occurs at the load equal or almost equal to PE. Okay. At which load the column snaps into two half wave modes. Okay, no more to read from there. Taking moments about the hinge, M is equals to FL over 2. So you can see here, as the column move laterally to this much displacement D, right? So F is coming from the stiffness of the spring multiplied by D. But then as the force, lateral force is exerting back in order to stabilize the column, and then you can determine the magnitude of the horizontal force at the top and the bottom supports to be F over 2. So you can take the equilibrium about this point. So FL over 2, this is L, F over 2. So take moment about this point, you get the moment going on this direction. Minus because the PE is producing moment into the counterclockwise direction. PE, which is at the buckling load, this PE is determined from pi square EI over this L square multiplied by the D naught plus D. The F is equals to KD because initially you have the original D naught. The original D naught is not contributing. This is the initial out of straightness, so it does not contribute to the bracing force because the brace has not been active at that moment yet, and this is the initial condition of your column. But this only deformation D, which is the extra from the D naught, okay, from this configuration to there, then the D is then used for the spring force calculation. Okay, so but the P has to be multiplied by this D naught plus D. So this is the driving moment and the resisting moment from the spring. So we equilibrate everything and then set them to be 0. And introducing the F equals to KD, as I mentioned already, one obtains the spring constant required to produce the full bracing, which is, it turns out to be K required, because if you have the full bracing, your P, the load, turns out to be the PE. It is the maximum possible load, okay, to be carried by the column. So K require, you just stuff in by KREQ, right, times the D. Put this on the other side. Okay, and then you divide through by the D, so this is D naught over D, and then D turns out to be just 1, like this. and okay, the D was moved to the other side, and then L and 2 was also moved to the other side, so you get this expression. And then for the ideal column, now the point is that the D naught is the problematic part, because if we have the D naught, then this whole thing is something, but you don't know, right? You don't know D naught and you don't know D, so the D is going to happen when the system buckles. So actually, if you really want to know D, then you got to do a lot more, not just this. So this is for the simplification. Now they give up and say that, okay, for an ideal column, D naught is 0. So we just delete that term out. And then the ideal stiffness, for the lateral support that is required for the ideal column, okay, let's put it like this, is equals to 2 times of PE over L. 2 times of PE over L, and well, that depends on the L, right? The longer the L is, the K will be smaller. This value is identical with that given by exact theory of elasticity supported columns. For that amount of rigidity that is required to make an elastic support. Okay. Required to make elastic support as effective as unyielding support. It will be observed that the rigidity required to produce full bracing in imperfect column exceeds that required for the ideal column. Of course, because this part here is non-zero, this is greater than 0, so you have 1 plus this part here. It turns out to be some number, but you don't know what number it is. That required for an ideal column. The larger the imperfection D naught, the more this is so. If one knows or estimates the initial imperfection D naught, which is being guided, for instance, by specified tolerances for crookedness, and if one stipulates the maximum permissible deflection, the immediately preceding failure. For example, D equals to this number, okay, conservatively. Okay, one can then compute the required spring constant, which is a measure of the rigidity of the bracing. Okay, and then you just put something in. The required strength of bracing. So you just need to impose the limit and D naught. Okay, that's the thing into the equation above. But now they are starting to talk about the capacity, and the capacity is given by the S. Okay, capacity is equal to the reaction force at or immediately preceding buckling. That is S required equals to K required multiplied by D. Do you know the D value? You don't know, right? This is the pain. You don't know the D value. S equals to K times D. The K required is coming from the development we had above, and then you multiply by D, then you end up with this. 2 times buckling load divided by L multiplied by D naught plus D. Now this part here is actually the K ideal. So PE can be determined, L is known, but the D naught plus D, what is that? if you limit the number to be small, like, oh, we're not going to exceed this number, small d value, and then the capacity will also be small as well. It can now be said that the full bracing has been provided if the K actual is greater than the K required. So nothing more than just don't provide less than the required stiffness, and likewise the strength for the actual system is greater than the strength in the required from the calculation. Column with 2 and 3 equal and equidistant supports will be considered briefly. Okay, so the paper here just develop some other cases further, because you see just only one support. Then they extend the idea into the cases where you have more than one support at the mid, about the over the between the top and the bottom supports. And yeah, it ends up to the case where you have like 4 equidistance. So this given in here, we can just continue this part tomorrow, along with the buckling analysis done by another approach. I think it will be very worthwhile. Things that it is quite classic to see all this paper and see all the effort which were done, whereas we have some better tools to use for the calculation of all of this. So the thing is that the K ideal for several cases, like for the cases where the lateral support is more than the previous one was developed, and then finally they come up with some number for the higher and higher number of supports. They also talked about the bracing of the beam case, which is finally we're gonna look into Ura paper, and that produce even better information than this one. But this is the original paper that is very classic, but then later on it is interpreted, it is reflected in the different aspects. Ura revisit the paper and wrote it out in the different point of view, which is very worthwhile, and it is very effective for the bracing design. The point, the issue is, which is remain in this paper, is about the D values. So in order to calculate the capacity, the strength, and the stiffness, the D is still there in place, and you cannot really get away from it. But Ura can make the life much better, so much easier, and later on all these things turns out to be not the problem anymore. Okay, I ran out of the energy a little early today, so we will continue tomorrow with this paper, and then we can extend probably to Ura's paper after the completion of this one. So we're gonna look into a couple cases. Actually, you can look into that before, because the material is already uploaded. Alright, okay. I think we wrap up today. Have a good day, and see you tomorrow, and continue from somewhere around here. Okay, bye bye.